Hey guys, welcome to a new video in Technodata. My name is Eric, and this is a part 2 for my previous video where I've shown you my emulator running some assembly programs, and today I'll be providing you further explanation into how it works under the hood. So let's begin. So if you watched my previous video, I said that my emulator can get input from the keyboard, and how does that work under the hood. So whenever you press a key or release a key, SDL receives this input, this information, and you can access the key that was pressed or released, and that will give you an ASCII key code. And then what I do is that I translate these ASCII key codes into USB key codes. So by doing that, I can recreate the full USB report, and then I can store these reports into a report buffer. And the reason for that is because the MOS technology 65C02 processor, it's an 8-bit CPU, so it can only read a single byte of data at a time. So a USB report is 8 bytes, so that would amount for 8 interrupts for a single USB report to be read. So that's why I use a report buffer, and I can store up to 8 reports in this buffer. So if I press a key and then I press another key and then another key, if I didn't have this buffer, I could lose information. You know, the CPU would not be able to keep up with all the keys being pressed, so you would lose information. So by buffering the reports, you can have at least guarantee that most of what you're typing is actually going to be read. Um, there should be better ways of doing this, or um, but this is the way that I found for now to read the keys and send them in a USB protocol format. Of course, I could use a uh, PS2 protocol, but I went for a challenge and tried to implement a USB protocol. So yeah, so it's a little bit of black magic happening happening here. So if this was real hardware, you would probably have an integrated device that could do the same functionality, but in this case it's software. So uh, you have the SDL layer that receives these inputs, and then you have a translation layer, which is a software layer, and then you have the actual emulation layer, which is the code of the emulator itself. So you can send these reports that are stored in the buffer 1 byte at a time into this integrated device here called a versatile interface adapter. um, and then this versatile interface adapter can send that information to the CPU. So the CPU receives an interrupt, and then it can run the correct interrupt handling subroutine and do something with that, which in my previous video basically consisted of activating specific pixels on the screen when specific keys were pressed. So yeah, I hope this has been clarified, how this works, how getting input from the keyboard works. I hope that has been made clear. So how does the storage works? So I've made the storage process to be the as simple as possible, as straightforward as possible. So Um, my storage device is called an SSD, which you guys probably know. It's a solid state drive, and it's called that way because I don't emulate typical hard disk behavior like spinning speed and other stuff. I wanted to make this as simple as possible, and it in fact is very straightforward. So how does that work? The SSD can receive instructions from the CPU. So you send these instructions to two versatile interface adapters, which in this case are VIA2 and VIA3. So you send byte 0 into port A. This is a 24-bit instruction. The size of the instruction that you send to the SSD is 24-bit. So that is 3 bytes. So you send the byte 0 to port A of this first versatile interface adapter. And then you send the byte 1 into port B. And then you send the byte 2 into the second versatile interface adapter into port A. So then you can get this full 24-bit instruction and send this instruction into the SSD. So the SSD can then process that instruction and set its registers and perform the desired instruction. So first, before everything else, you need to set up the DSR register, which stands for Destination Source Register, and that's the register that holds the value of the first memory address on the RAM where you are going to perform I/O operations. So let's say that I set up the DSR to hold the value of A000. So now it holds this value. Okay. Then I need to configure the AR register, which stands for address register. This is a 22-bit register, and with this register you can access data on the SSD. You can access up to 4 megabytes of data. So this SSD can store up to 4 megabytes of data. Okay, so you need to set up the AR register, and this is going to point to the first address on the SSD. So DSR points to the first address of the I/O space on RAM, and AR points to the first address that you're going to read, or the first address that you're going to write on the SSD. And then you have the offset register, which is this OR register here, which is a 11-bit register. So you can have a number from 0 up to 2047, if I'm not mistaken, because I cannot see the number here because the resolution of the image is low, but you get the idea. So for example, let's say I want to read 2000 kilobytes of I want to read 2 kilobytes, sorry, of data, which is the maximum number you can do in a single instruction. So let's say I want to read from the SSD. So then I send 3 instructions. So I set up the DSR, then I set the AR, then I set the OR. By the way, DSR is only set once, so every instruction after that is going to be either setting the AR or the OR. Okay. So let's suppose I was going to make a read operation. Yeah. So the SSD is going to read what's stored in its memory, and it's going to place that onto RAM. So that's called DMA, which means direct memory access. Yeah. So let's suppose the SR is set as A000, and I'm going to perform a read operation of 2 kilobytes. So it's going to read 2 kilobytes of its memory. For the sake of simplicity, let's imagine that AR, the address register, is set to 0. So 2 kilobytes means it's going to read from address 0 on its internal memory, and it's going to end the reading process at address 7FF, which is 2000 bytes in 2047, excuse me, bytes in hexadecimal. And it would put that information in memory addresses counting from A000 up to A7FF. So yeah, that's what a read instruction would do if I was going to get two kilobytes of data. And if I was going to write, it will do the same thing, but instead of reading, instead of sending to RAM what is in its memory, it would read what is in RAM and would store it in its memory. So, well, that's it. As I said, it's pretty straightforward. It works in a pretty straightforward way. One more thing about the instruction. It's a 24-bit instruction, but the last 2 bits are what actually tells the SSD what to do with this information. So if the last bit is set as a 1, this means that the instruction is ready to be executed. Why is there a bit for that? Because as I explained previously, the MOS Technology 65C02 processor is an 8-bit CPU, so it can only send 1 byte at a time of the instruction to the SSD. So so the SSD needs to wait until all the bytes of the instruction to be executed have arrived. So the way you tell it, it's by setting this last bit, which means, yeah, the instruction, the whole instruction is finally here. You can execute this instruction. And bit 22, counting from 0, which in this case would be the 20th third bit, I think. This is going to be the bit that tells the SSD whether it's a write operation or a read operation. So yeah, that's about it about the instruction. I hope I made myself clear, and I hope I didn't make as much confusion as I think I did in my previous video. Again, sorry, I'm not a native English speaker. I'm a native speaker of Portuguese and Brazilian, so if sometimes it's difficult to understand what I'm saying because of my accent, or because I make very long pauses when I'm speaking, sorry about that. Yeah. Well, that's it. I hope you enjoyed the video. Like and subscribe, and I see you in the next video.